Have you ever stopped to wonder why the world around us looks and feels exactly the way it does? I mean, why do some things completely shatter when you drop them, while others just bend? Or why some objects get blazing hot out in the sun, while others stay perfectly cool? Well, it's not magic. It is pure foundational engineering. Welcome to This Explainer. Today we're unpacking the properties of materials, the invisible, hidden architecture that literally dictates the construction of our everyday lives. Okay, let's dive into this. Because here's the thing. Everything we build, touch, and use basically comes down to this one idea. All those big macroscopic properties we're going to explore today, they actually start right at the microscopic level. The behavior of any material is entirely dictated by how its atoms are arranged. It's kind of like a giant dance. How tightly those atoms hold hands, how freely they let energy flow between them. Those tiny, invisible bonds scale all the way up to determine whether a material is going to be used to build a massive skyscraper or just wrap up a chocolate bar. So, here is our scientific roadmap for today. 1. The hardness hierarchy. 2. Bending and shaping materials. 3. Tensile strength under pressure. 4. Conducting power and heat. And finally, 5. Selecting the right material. Section 1. The hardness hierarchy. Resisting surface wear. Before we get into the actual rankings, we really need to nail down a clear definition. Because in materials science, hardness doesn't just mean, does it break when I drop it? That's actually something else entirely. Hardness is strictly defined as a material's resistance to surface deformation, scratching, or indentation. Think of it like this. If I scrape material A against material B, the one that leaves a scratch on the other, that's the harder material. It is literally a battle of the surfaces. And here's exactly how that battle shakes out, ranked from hardest down to softest. Sitting right at the undisputed top is diamond, which is completely unmatched in its ability to resist scratching. Just below that, we have industrial heavyweights like cubic boron nitride and carbides, and then hardened steels and cast irons. But as we move down into much softer territory, we hit metals like copper and aluminum, plastics like acrylic, and finally, right at the very bottom, lead. Lead is so incredibly soft, you could easily scratch it with a standard pocket knife. Looking at that extreme top spot brings up a super fascinating practical question straight from our source material. We all know diamonds are very hard, but what else could we realistically use them for besides, fancy jewelry? Take a second to really think about that. If you had your hands on the ultimate scratch-resistant, non-deforming material, how would you put it to work in the real world? Now, what's really interesting about this is how we actually apply that luxury gemstone to heavy, messy industry. Because of their absolute top-tier hardness, diamonds are frankly perfect for cutting, drilling, and grinding. Engineers will actually embed tiny diamond particles right into saw blades and drill bits so they can effortlessly cut through concrete, stone, and hardened steel. It's the ultimate industrial tool, and it's all thanks to that microscopic atomic arrangement we talked about. Section 2. Bending and shaping materials, ductility, and malleability. Now, to understand how we shape things, we have to clearly distinguish between two properties that sound similar but in practice are very, very different. The first is ductility. This is a material's ability to be pulled or stretched out into a wire without snapping. The second is malleability, and this is the ability to be pressed, rolled, or hammered flat into sheets. So basically, pulling into a wire versus pressing into a sheet. Let's look at the rankings for both of these. Notice anything pop out? Gold sits firmly at the absolute top of both lists. It is, without a doubt, the ultimate shapeable material. Think about this for a second. You can stretch a single ounce of gold into a wire that's literally miles long. Or you can pound it into a sheet so incredibly thin that it actually becomes translucent. No way, right? It's amazing. Silver, aluminum, and copper follow closely behind. But check out the bottom of the list. Steel is highly resistant to being pulled or hammered. It is just incredibly stubborn and rigid. So, let's test this knowledge with an object I guarantee you've held 1,000 times. What material makes up soft drink cans, and why do we use that specific material over everything else? Think about those properties we just ranked. The answer, of course, is aluminum, and it's chosen specifically because its extremely high malleability means it can be easily pressed and stretched into those thin, lightweight, but durable little cylinders. A harder or less malleable metal would just crack and shatter under all that intense manufacturing pressure. But aluminum, it yields perfectly to form the billions of cans we use every single year. Section 3. Tensile strength under pressure. Handling pulling stress. So tensile strength is basically all about how much pulling stress a material can take before it simply snaps in half. And wow, look at how our order has completely flipped from the malleability list. Steel, which was so stubborn and unyielding when we tried to shape it, now reigns supreme as the strongest material under tension. Following steel, we've got copper, aluminum, zinc, and then, yep, lead down at the bottom again. This brings us to a massive, real-world engineering challenge. Imagine you're building a massive suspension bridge. You are essentially hanging thousands of tons of concrete and asphalt right in midair. Based on the rankings we just looked at, what material absolutely must be used to support that bridge, and why? And this brilliantly illustrates our point. Just look at the staggering scale of the Millau Viaduct. Those colossal cables holding up the road, they absolutely have to be steel. Steel is the only correct choice here because of its completely unparalleled tensile strength. It's not going to stretch out like gold would, and it certainly won't snap under the immense, constant pulling force of gravity and heavy traffic. When you literally need to hold the world together under tension, you use steel, period. Section 4. Conducting power and heat, electricity and heat. When it comes to conducting electricity and heat, we're back to those atomic arrangements, but this time they're working in overdrive to let electrons pass right through. The absolute top-tier conductors are silver, closely followed by copper, gold, and aluminum. But there's a really cool side note here. Some metals also boast highly unique magnetic properties. The big three magnetic elements in the universe are iron, nickel, and cobalt. Basically, any compounds containing those elements are going to be magnetic too. Okay, I've got a final practical mystery for you. Think about the walls of the room you're sitting in right now. What material is used for the standard electrical wiring inside them? And based on that top conductors list we just saw, why on earth don't we use gold or, say, lead? The answer perfectly captures the day-to-day reality of engineering. We use copper. But why? Because copper balances incredibly high electrical conductivity with practical cost. Sure, silver and gold might be technically fantastic conductors, but they are incredibly expensive. Wiring a single major city with gold would literally bankrupt a nation. And lead, well, it just conducts too poorly to be effective at all. So copper hits that absolute perfect sweet spot.
Section 5. Selecting the right material, a balancing act.
So the crucial point is that out there in the real world, materials are almost never selected for just one single trait. It's a hugely complex balancing act. Engineers have to weigh hardness, ductility, density, melting point, and conductivity against all those strict economic factors, like the cost of raw materials, suitability for recycling, and how easy it is to actually manufacture. It is basically a giant, three-dimensional puzzle. As our source material so elegantly sums it up, the physical properties of a material have a large part to play in its selection for a particular application. That sentence right there, that is the central thesis of all materials technology. The microscopic traits of a material directly dictate its macroscopic destiny. I'm going to leave you with this to ponder today. Look around the room you're in right now. Really look at your phone, the desk, the window glass, your coffee cup. What invisible physical properties actually determined the materials of those objects sitting right in front of you? The next time you pick something up, remember, its very existence in that specific form is a total triumph of material science. Thanks so much for joining me on this explainer, and keep questioning the world around you.